science projects.
I see smart people. This is obviously a pithy title for a talk, so I'm going to just scoot ahead here. I direct the Human Computation Institute and lead the Eyes on Owls project. You know, as anyone in citizen science knows, a project is the people who are in it. So I want to make sure that you know, the folks on our team who have made a huge difference in this project and that I'm fortunate to work with, that you get a chance, and I'm sure you recognize some of them here. But it's not just the team, as you know, it's what I call team humanity. In particular, so we had a hangout recently to kind of celebrate a recent success that we had with the project in terms of participation based on new team feature. And the folks that are circled are participants, folks in the community who made huge contributions as contributors. And as you can see, they're part of the conversation, and we think it's important for them always to be part of the conversation. So, and also I noticed, so for any of my contemporaries, that for some reason it's just, you know, the Hollywood Squares thing when they started noticing the circles and that I was winning. You know, what I'm hoping to do, I can't get into the nuts and bolts in the amount of time we have, but I just want to talk about some problems that we had and the way that we went about solving those problems, and I'm hoping that you know, that'll be generally useful to folks who are either embarking on a new project that has similar characteristics to ours, or who's interested in improving the efficiency of their platform. So the scope of these problems, the context is crowdsourced classification. So, you know, the idea is a participant is shown something and they have to decide which category of things it fits in. If it's an animal, you know, what the species is the class, and if it's a galaxy, the type of galaxy. And in our case, in the Stall Catchers game, which is about accelerating Alzheimer's research, you know, we show a blood vessel and we just ask people to tell us, is this blood vessel flowing or is it stalled? And I'm not going to talk a lot, you know, you can go to stallcatchers.com and try playing it. I would encourage you to do that, of course. In our case, it's two-choice classification, which is kind of the same thing as detection in a sense. So one class is the thing you're looking for, and the other class is that it's not the thing you're looking for. And so just in principle, even though we've applied our approach to two-choice classification, you could take any multi-class problem and reduce it to that, you know, using you know, kind of the theoretical model, and come up with a similar approach, because each class is then with respect to all other classes. So that's all I'll say about that. So the first problem we were trying to solve is this problem of random responders. So, you know, one example of that is obviously a web bot. So there are folks out there who I guess have some spare time, and they're just interested in racking up a score on anything they can find, and they'll create a bot and see if the bot can put them to the top of the leaderboard. And we, you know, just an aside, so sorry, I'm going to apologize in advance. Some of my kind and close colleagues have informed me that I'm occasionally long-winded. I will try not to go down too many rabbit holes, also out of respect to the next speaker. Anyway, we had some folks early, it's just an interesting, so we had some folks early in the project who decided that if they could elevate onto the leaderboard and they coordinate their behavior, they could change their usernames and put political messages up there. And they actually did that. And then we realized that maybe we shouldn't allow people to change their usernames. So that was kind of an easy fix. But so there are kind of malicious actors. You know, random responding can happen in a lot of ways. And anyone who has a cat knows this is not just a joke. I mean, this kind of thing actually happens. And then there are, again, bad actors, and as we all know, the best way to remain anonymous on the internet is to wear a ski mask when you're surfing the web. So what's exciting to me about this is that my dissertation actually ended up being a useful thing. And anyone who's done one, you always wonder, like, is this really going to make a difference any time in my life? And it happened, I don't want to say how many years ago, but so I was studying psychophysics, and then when I came to this project and this problem, I realized, whoa, this actually could be useful. There's this whole field, and folks who are in the field of astronomy or medical research, they're not necessarily aware of psychophysics, but a lot of work has been put into developing methods to measure how people respond and to be able to kind of tease out how cognition works in exactly the kinds of classification tasks that we're studying here. So the big question that psychophysics tries to answer is, given a stimulus and the response, and knowing what those two things are, how can we, what kind of a cognitive model can we infer from that? And so a few decades ago, some folks had this kind of brilliant insight, which is, so in the field of radar engineering, they had this problem, which is that there's a radar operator and then the radar equipment. And the radar equipment has a certain amount of sensitivity, so a blip shows up, and hopefully it shows up soon enough. This is like, imagine wartime, enemy aircraft, that kind of thing. And then the operator has to decide, is that a real enemy aircraft or is that a pigeon, for example. And there's a cost and benefit associated with making the right or the wrong decision. And there are two different kinds of mistakes you can make. So one mistake is to say that this enemy aircraft is a pigeon, so you don't launch a defensive kind of maneuver, and the consequence there is obvious, that you get attacked. And then the other kind of mistake you make is that you assume the pigeon is an enemy aircraft. You launched 3 aircraft to go and attack the pigeon, and you've wasted a lot of time and resources. The key insight here is that with the signal detection theory, anyone who has seen or used an ROC curve has used signal detection theory. That receiver operator curve, ROC, comes from the radar engineering field. The key insight is that you can tease apart the sensitivity of the apparatus, the radar equipment, from the bias of the operator and the utility function the operator is using to make these decisions, the cost utility function. And cognitive scientists said, we can apply this to these indirect methods we're using, and we could actually figure out when somebody's answering classification questions, we can separately measure their sensitivity and their bias. They're actually, with some very basic underlying assumptions that are fairly easy to measure and meet, that they're statistically independent. And this becomes very powerful and helpful for what we're trying to do. And so I just, Google's great. It turns out there's actually, at one time there was a very measurable cost for making a mistake and taking out a pigeon, particularly if it's a homing pigeon. So it turns out that when we used this approach and applied it, sorry, I need to back up a second. So, spoiler alert, it did work, but let me tell you what actually worked. So what we did is we measured the sensitivity using signal detection theory, and we applied it to our scoring function. And the idea is that if you're randomly responding, your sensitivity will always quickly go to 0. So any web bot, any pet cat that starts tapping is going to drive your sensitivity down to 0 quickly. And so anyone who's trying to implement a random response approach or other kinds of ad hoc response approaches will quickly lose their sensitivity, and if the scoring function is multiplied by the sensitivity, then the points you get for each annotation will be 0. And so we ran some simulations, and I'm not going to take time to explain the graph, but it worked. So that was an exciting an outcome. And one of the other sort of benefits of this is we applied a moving window on sensitivity because some of our end users are Alzheimer's patients. We want them to be empowered to make a difference in their own potential future treatment opportunities. And there's this effect in Alzheimer's disease called sundowning, which anyone who's been sick, you know that sort of late afternoon, evening, you think you're over your cold, but then you start to feel worse. And in Alzheimer's disease, this manifests as kind of a fuzziness in cognition that happens that time of day. So what we want to do is be able to kind of appropriately tailor how we incorporate their data depending on their level of alertness, and not just for them, but for anyone. So someone who might have a very high sensitivity, one day it sits down with a beer to annotate, and their sensitivity might drop a little, and we just want to know about that for the benefit of the data. Problem in a lot of these kinds of classification projects is how do you combine crowd answers, or how do you combine individual answers into a single crowd answer that's expert-like? This app has probably appeared on more talks than any other. I love Malaria Spot. Is anyone from Malaria Spot here in this? I think someone's here at CSA, but it's a wonderful idea. So they had to test out how many annotations do we need, to analyze this blood smear and figure out if this person has malaria. How many different answers do we need to combine to have an answer as good as a trained pathologist? Because of course that's the purpose of it, is to use the crowd to accelerate that and replace something that would otherwise be time consuming. And they found that their magic number was 23. And they did a validation study to determine that. So we went ahead and conducted our own validation study, and what we determined was that, and you can see in this graph that with 5 annotations per vessel, that we had one level of. So I'm using sensitivity and specificity as metrics for the quality of the data, and that at a certain point, right after about 15, we crossed the research threshold. So the research threshold is what our biomedical collaborators told us was what was needed. Sorry, I'm realizing that, I don't know, maybe I'm hitting the wrong button. I think every time I hit the button, it skips 2 slides ahead, and that's why I'm kind of missing some key points. So I'll try to, I don't know. In any case, what we discovered was that our magic number was between 15 and 20, but obviously for the benefit of the analysis, we had to be conservative, so we used 20. So that kind of solved the second problem, and gave us confidence moving forward that the crowd answers were valid. So our third problem was that, okay, so you can imagine that when you're collecting 20, it's kind of the strategy there is it's the worst case scenario. There are probably other times if the responders have a very high sensitivity level, you don't need all 20 of those responses. You might need only 5 very sensitive annotators to get an expert-like answer. But the question is, how do we improve our efficiency, kind of taking that sort of thinking into account? So why would we want to improve our efficiency? So there's the ethical obligation, to the crowd. Anyone who's spending a lot of time on this, and we have users who spend several hours a day actually annotating vessels, and we think about them. We feel a sense of loyalty to them, and it's unethical to waste human time. And then the purpose of our project is to get to a cure or a treatment for Alzheimer's disease as fast as possible. It's a horrible disease, and it affects obviously not just the patients, but the families, and every second that there isn't a treatment, this is a terrible hardship. So we feel very motivated to solve this problem, and we've been working hard on it. So our strategy is assign weights, which we're doing using our sensitivity measure, and then to develop a way, to have a kind of a way to measure sensitivity, not just in an individual, but in a collective mind, right? And so there's a precedent for this, and I guess in Galaxy Zoo number 2, there are folks here who are going to correct me when I mess this up, that there was this notion of, I think it's consistency, which is like a proxy or one way to say, you know, this person's answer is very much like all the other answers about this particular annotation, and that's the way that we assess their expertise. And so this is kind of a way to, you know, again, assess something like the sensitivity that we're using. And then in this this other project, the one that had the really high bar of participation, was it Space Warp, or if I'm saying it right? And in that case, their strategy was, to reduce the number of annotations, was to use a stopping rule and kind of do a random walk and say, once we've collected enough evidence for this, we're going to stop. So what we've done in effect is, and I stole this from Lucy's slides, I almost just used her, you know, talk, and I was just going to talk to it, but I thought that wouldn't really be ethical. So, so we sort of combined this approach, and again, our idea was to kind of extend this this model of measuring sensitivity at an individual level to measuring it in the collective mind. So, so that's what we did. We came up with a collective sensitivity measure, and so you know, we implemented that, and basically after each annotation we accumulate a collective sensitivity. When that collective sensitivity reaches a threshold, we stop collecting annotations. Why would you need to collect more if you know that that you've achieved, you know, that level of sensitivity, which means you have enough information to actually make a good response. And as you can see, what we found is, at least with the same validation data that led us to our original magic number of 20, that we were able to, using this method, reduce that to only 4 annotations on average. But it kind of brought us to a new kind of magic number, because in this case it's not really 4 annotations. It's not like we say we're going to collect 4 and stop. It's a variable number. So the new magic number is what's the level of sensitivity that the collective mind needs to reach before we stop, and then that governs what that number of annotations is. And so on average it's 4, but sometimes it's 2, and sometimes it's 10. But in all cases it's a lot less than 20, which is what we were aiming for. And so it's really, and we're applying this to some new data sets now. It turns out that it's a little higher than an average of 4. It's more like an average of 7. But relative to 20, it's about a 3-fold improvement in efficiency. So that's all I have to say. I don't know if we're probably out of time, which is why I just want to invite you to, you know, find me later if you're interested in talking more about this, and if you have related methods, I'd love to learn about that as well. So thank you.
All right. Next up, we have Robert Pastel talking about developers and project leads working together.
Thank you. Help me with